Alright, so this video is going to review dimensional analysis. We're going to start with some basics of dimensional analysis and kind of work our way from there. When you're always doing dimensional analysis, you want to make sure you identify what you're starting with in your problem. Next, you want to set up your conversion factor so that your units will cancel out. Sometimes you may need multiple conversion factors, as it notes in step 3, until you get all of the units that you need to remove are gone and the units that you're trying to find are set up correctly. Then you're going to multiply across and divide by your denominator and apply your sig fig and rounding rules. So this chart here I made a separate PDF of that is available on Classroom. You do need to know these prefixes. You need to know what they represent and be able to do conversions with them. Because there are a few more than what you had to do in your first year class. There is a mnemonic at the bottom of the page. I promise it's never happened, but if it helps you keep them in order, then hopefully it will be of use to you. Many kids have dropped over dead converting metric measurements in problems. Over is your placeholder. Anything above over is representing a prefix that is bigger than your base quantity, such as 1 kilogram has 1,000 grams. Well, below 0, those prefixes represent quantities that there are multiple of that could fit into one of the base units, such as 1 meter has 100 centimeters. So our first example is going to be pretty straightforward. We're just going to go from milligrams to grams. Just as a quick review of what you've done previously. Start with what you're given, the 3,800 milligrams. You want to make sure that you get those milligrams to cancel out by putting them in the denominator, and the grams that you're trying to find go in the numerator. From our chart, we can see that one of the base units is equal to 1,000 of the millis. 1 gram is 1,000 milligrams. I did use prefixes on this chart, grams on this chart. You could use any unit, so these could be meters, liters, seconds, amperes. That part doesn't matter, so don't get too stressed out about it. Well, you can see this one all the way through now because I already showed it to you. The 1,000 would go with the milligrams, the 1 goes with the grams, the milligrams cancel out. Multiply and divide gives you 3,800 over 1,000. In terms of sig figs, this does not count as sig figs. We talked about previously, it's a defined quantity. So it's only the 3,800 that has an effect on your sig figs. It has 2, so we want 2 in our answer, so we would write it as 3.8 grams. Example 2 is going to require a couple of conversions because you're starting with one prefix and you're going to another. We're starting with decis. We have 0.00475 deciliters, and we want to know how many microliters are equivalent to that. Now, according to the chart that I just showed you, I'm going to show this one up front for a second, but if you go take a look at this chart, you're going to see that there's 1 gram equal to 10 decigrams, so 1 liter is equal to 10 deciliters. And then with micro, 1 gram is equal to 1 million micrograms, so 1 liter would be equal to 1 million microliters. Both of the prefixes have in common the base unit, grams on this chart, but liters for our problem. So we're going to need 2 steps to solve this problem. The first step is going to be to remove deciliters from the problem, and then the second step is going to be to convert that base unit into microliters. So we start with our 0.00475 deciliters. We use our chart to come up with a conversion between deciliters and liters, and according to our chart, 1 liter has 10 deciliters. That gets rid of the decis, and now we're needing to get to microliters, so we need to cancel out the liters by putting them on the denominator and putting microliters up top. And according to our chart, 1 liter is equal to 1 million microliters. So the liters are gone. We've got to the units that we want to have in our answer, so we multiply and divide. Again, the defined quantities for deci and micro do not affect sig figs. 0.00475 has 3 sig figs, so I want 3 sig figs in my answer, 475 microliters, or I can write this in scientific notation as 4.75 times 10 to the second microliters. Our third example is going to have something a little bit different. You're going to do a calculation, and then we're going to do a conversion. We're going to take a compact disc. I'm not sure why I did K for one and C for the other, my apologies. And it has a diameter of 11.8 centimeters. We want to know what the surface area of the disc is in square centimeters. And then we also want to know what it is in square meters. Now, surface area is just like the area you would do of a circle, because that's what a disk is, pi r squared. So since we were given a diameter, we're going to need to cut that in half, since the diameter is the equivalent of 2 radii. And so we would take half of 11.8. That is a measured quantity, so we want to keep it thick figs. When we cut it in half, that 2 we're dividing by is define a value. So we have 5.90 centimeters squared. And when you multiply pi times 5.9 squared, you go ahead and get your quantity in centimeters squared, 109. So that's the first part of our problem. The second part is going to meters squared. And you can actually do that by keeping it in centimeters squared. The conversions we have only go from centimeters to meters. And we know that there are 100 centimeters for every 1 meter. Well, that will take care of one of the centimeter units in centimeters squared, but it doesn't take the place of the other. So you would need to do one more conversion to get rid of that 2 that's on centimeters by just repeating your conversion again so that you have meters times meters in the numerator and centimeters times centimeters in the denominator. At this point, you are in meters squared, so you can multiply, excuse me, and divide. You have 109 times 1 times 1, and then you're going to multiply 100 squared, and that would give you 1.09 times 10 to the negative second meters squared. Now, there are other ways to solve this problem. You could just go ahead and square this conversion. This was a way I was shown at Shenandoah, and it just seems to help the students see that you have to do it twice. Sometimes people neglect to square the 100 when they just do it in one step. But I will show you one step in class, and if you prefer to do it that way, that's fine too. So this time we are told that soft drinks can be sold with volumes of 1,500 milliliters. And I want to know what this volume would be in cubic decimeters as well as cubic meters. Well, I'm not going to ask you to switch units without giving you some sort of relationship between them, and you cannot get this relationship from your chart. It happens that 1 milliliter is the equivalent of a centimeter cubed, and that 1 liter is the equivalent of a decimeter cubed. We didn't want to find anything with centimeters, and I know we have milliliters to start with, but I think it's probably going to be a little bit easier if we go ahead and get to liters, and then work our way to decimeters cubed, and then meters cubed. Now, that is one way you could solve this problem. There are plenty of other ways. So if you chose to go another way with this, as long as you get the answers that you're supposed to have at the end, and your work makes logical sense, I am not going to penalize you. So just my choice was to start with the 1,500 milliliters and to go ahead and convert that to liters. From our chart, we know that there's 1,000 milliliters for every liter. And now we are at liters, and that is the equivalent of decimeters cubed. So if we have 1.5 liters, we also have 1.5 decimeters cubed. So that's the first part of this problem, at least the way I've chosen to solve it. The next part, we're going to go from decimeters cubed to meters cubed. Well, just like we did previously, we know that there's 10 decimeters for every 1 meter, but because we have 3 of those decimeter units, we're going to need to do that conversion 3 times to get each of the decimeters to go away. So those 3 decimeters in the denominator will cancel out the decimeter cubed in the numerator, and now we have 1.5 times 1 times 1 times 1 over 1 times 10 times 10 times 10, and that would be 0.0015 meters cubed, or 1.5 times 10 to the negative third meters cubed. Example 5 is the density of zinc is 7.14 grams per centimeters cubed. I want to know what the density would be in milligrams per millimeters cubed and in kilograms per decimeters cubed. Again, there's more than one way to solve this problem. I'm going to go ahead and do the conversions all in a single line, but if you want to split them in half, do the numerator and the denominator separately, and then divide by them at the end, you are welcome to do so. I'm going to start by doing grams to centimeters cubed, and because grams and milligrams only are going to require one conversion, I'm going to go ahead and switch that over. And then I'm going to worry about the centimeters cubed. So I have 7.14 grams per centimeters cubed. I know that there are 1,000 milligrams for every 1 gram. So grams needs to go on the bottom since it's in the numerator to begin with. Milligrams goes in the top. And that leaves me with milligrams per centimeters cubed. I'm not going to solve it yet though because I need to get to millimeters cubed. And I know that for every 1 centimeter there are 10 millimeters. Since centimeters are in the denominator to start with, to cancel them out, I need to put them up in the numerator. And that's indeed what I'm going to do once I solve this one through. Sorry, I didn't think I solved it. I'm going to take 1 centimeter for every 10 millimeters. And I'm going to do that 3 times so that the 3 centimeters that are here in the denominator cancel out. And now I would take 7,140 milligrams and multiply it times 1. And I would divide it by 10 cubed. And that would give me the same answer I started with, 7.14 milligrams per millimeters cubed. So because I changed the numerator by 1,000 going from grams to milligrams, and I changed the denominator by 1,000 going from centimeters cubed to millimeters cubed, it ended up being a wash, and the quantity was the same as it was to begin with, even though they were different units. This does not tend to happen unless you have units in the numerator and denominator that both require conversions, and even then it's not going to happen all the time. To continue with this one, now we're going to go from grams to centimeters cubed to kilograms per decimeters cubed. So I'm going to start by going from grams to kilograms, leaving the centimeters cubed alone, and then I'm going to use centimeters cubed to get me to decimeters cubed. So this time there's 1,000 grams in every 1 kilogram, so the 1,000 has to go in the denominator, the 1 goes in the numerator, and that leaves me with 0.00714 times 7.714 kilograms per centimeters cubed. To get to millimeters cubed, I'm going to take that quantity, and because again there's 1 centimeter for every 10 millimeters, the tens will actually go, I flipped it, my bad. Centimeters cubed and decimeter cubed. This time centimeter is actually smaller than decimeters. Deci's 1 away from the placeholder. So there are 10 centimeters for every 1 decimeter. So the 10 centimeters needs to go in the numerator, and I need to do that 3 times. So you may notice that we had 1,000 at the top that we divided by, and we have 1,000 we're going to multiply by. So this too will actually end up being still 7.14 kilograms per decimeter cubed. In the one previous, we made the quantities get smaller. In this particular one, we made the quantities get larger, but because they changed by the same proportion on the numerator and denominator, the actual value did not change for that density in those units. So hopefully that'll help you with part 2 of the summer assignment. If you have any questions, please don't hesitate to contact me.